Hello Math Humans, we're going to do 4.4a today. We're going to be talking about the Fundamental Theorem of Calculus. Our objectives are that we're going to use the Fundamental Theorem of Calculus, the mean value theorem for integration, and then we're going to find the average value over a closed interval. So the Fundamental Theorem of Calculus says that if f is continuous and differentiable, then the integral from a to b of f of x dx is going to equal capital F, which means we're talking about integration of a minus f of b. Okay, so that is the formal definition amended a little bit for the Fundamental Theorem of Calculus. So let's just jump right in with some examples. So for example number 1, I want to evaluate, and we're going to do these by hand. You could do them in your grapher, and I've shown you how to do that, but we're going to be using doing it by hand to make sure that you understand and are good at evaluating integrals by hand. This is asking you to find, without saying, the Fundamental Theorem of Calculus, which is basically the area under the curve from 1 to 2. So this is going to be x cubed over 3 minus 3x, and we're going to evaluate from 1 to 2. And so this is going to be 2 to the third over 3 minus 3 times 2 minus 1 to the third over 3 minus 3 times 1. And if you do that math, you will get 8/3. Okay? Is that true? I lied. That's not true. You get a negative 2/3. So for right now, it's important that we're going to do these by hand just to make sure. If it's a no calculator version of a test, then you would be required to show all of the work. If it's a calculator version of the test, I would just put this in my calculator and off we go. All right, the second example also says the same thing. So example number 2 says to evaluate, and I'm going to integrate from 0 to pi over 4 secant squared x dx. Well, the integral of secant squared is going to be the tangent of x evaluated from 0 to pi over 4. So this is the tangent, can't see, sorry, the tangent of pi over 4 minus the tangent of 0, okay? The tangent of pi over 4 is 1, the tangent of 0 is 0, and so this is 1. Remember, when we're evaluating a definite integral, it's always going to be top minus the bottom, okay? Example number 3, I think we can squeeze it down here on the bottom, says evaluate the integral from 0 to 2 of 2x minus 1 dx. The reason that I included this is because remember that evaluation, the Fundamental Theorem of Calculus, says that this function has to be differentiable. But this is an absolute value, so technically it's a piecewise, and I really can't take the derivative, but I can still calculate the area under the curve. So let's look at the graph. So it would, my x-intercept is a half. We're going to integrate to 2, and so my graph is going to look something like this. It crosses here at 1, and we're trying to find the area under the curve from 0 to 2. Well, the interesting thing is, because I can't take the derivative at a sharp point, then I need to split up my derivative, my integral. So I'm going to integrate from 0 to a half, and I'm going to do, because it's an absolute value, the slope of this piece is negative, so I'm going to do the negative 2x minus 1 dx, and then I'm going to integrate from 1/2 to 2, and that slope is positive, so I would do the positive portion of the absolute value, okay? And so I'm just going to rewrite this one. This is the integral from 0 to a half of 1 minus 2x dx, and then here's my second integral. So even though technically I can't integrate the function, I can split it up and evaluate each piece separately. Another thing to notice is I could find the area under the curve just by doing my area calculation. Because the area of a triangle is 1/2 the base times the height, and I could do it with just straight geometry. But I'm just going to set these up. So if I come back from my integrals, this is going to be x minus 2x squared over 2, evaluated from 0 to 1/2, plus 2x squared over 2 minus x, evaluated from 1/2 to 2. And technically, I would probably want to put in my little parentheses. And again, I'm assuming you are brilliant at this point and that you can do those calculations, and when you do, you will get 5/2. Remember that it's always top minus the bottom on a definite integral. All right, the next concept that we want to talk about is average value. And it's really important it helps if you spell it right, when you're doing calculus problems, if you read the statement or the directions well. So in general, when I want to calculate an average, it's going to be the sum of the things that I am taking an average of divided by how many. So the same is true in calculus. The average value is 1 over b minus a. I'll explain the formula in a minute, f of x dx. This portion is the sum of all of the pieces. This is how many. So the average value of a function over a specific interval is just the integration of the function divided by the interval. So it's the sum divided by how many. All right, example number 4 says find the average value of f of x is equal to 3x squared minus 2x on the interval from 1 to 4. Okay, we've talked about we need to label our work when we start, so I'm going to write that the average value is equal to 1 over 4 minus 1 times the integral from 1 to 4 of 3x squared minus 2x dx. This is what I mean when I labeled, I'm showing my work. I showed it's 1 over b minus a, and then I have my integration. So this is 1/3 times 3x to the third over 3 minus 2x squared over 2, and then evaluated from 1 to 4. If I clean this up a little bit, it makes my life a little bit easier. This is x cubed minus x squared, evaluated from 1 to 4. And then I would just substitute in my values and do top minus bottom. This guy can stay outside, so this would be 1/3 times 4 cubed minus 1 cubed minus, and I'm going to put it in parentheses, 1 cubed minus 1 squared. And then when I do that math, I would end up with 16. So the average value of the integral f of x dx is going to equal 16. All right, the next concept that we want to talk about is the mean value theorem for integrals. And if you'll remember, the mean value theorem for derivatives, the MVT for derivatives, says that v prime of t is equal to s of b minus s of a over b minus a. For integrals, it's going to be an existence theorem, which means that the possibility exists, and it's going to be the integral from a to b of f of x dx is going to equal f of c times b minus a. Okay, and that would be the mean value theorem for integrals. We're not going to do an example on that because we don't use that one quite as much, and I think it's fairly straightforward in its application. Alrighty, that is it for today. I will see you soon.